So thank you very much for inviting me. I'm very happy to be here. I'm very excited to be speaking to a group of people that I don't normally get to speak to. That's great. As Jared said, I'm going to talk about a lot of different problems, kind of real world problems, and describe some of the mathematics in them. But there's two things I'd like to do first that are not that. So the first thing I'm going to talk about is a little bit of my history, and I'm going to do that because I've got 2 points that I want to make. When I was at school, I really loved doing maths, but I didn't know you could do it at uni. What I wanted to do was environmental science, and I wasn't quite sure. So I did a Bachelor of Science, and in first year I did a bunch of different things. I did maths and physics and chemistry and biology with the intention of doing environmental science. But at the end of first year, I decided actually I like physics a lot more than biology and environmental science. So that's what I did. I did physics with the intention of coming back to environmental science. So I did a Bachelor of Science with a double major in theoretical and experimental physics. And then I went to Wollongong and did an honours and masters in environmental science. Now that degree was 2 years long. The first year was coursework in environmental science, and at the end of the first year I decided actually I don't like environmental science at all. The head of school knew this, and he sent me to his friend in mathematics to supervise my project, which is what happened in the second year. So I did a project in mathematics for my honours, and it had applications in environmental science, which kind of kept that side of me happy. And I really enjoyed that mathematics there, and so then I went on to do a PhD in applied mathematics. And then I've stayed at uni ever since. I never went out and got a real job. So now what I do, everything that I do in my job can basically fall into 3 categories. The first is teaching. I teach maths students in the maths degree, and I really love doing that, but I also teach students in other degrees, as Jared said, that aren't really always keen on doing maths. So I taught the engineering students for many years, and then more recently I've been teaching the health science students. They do one course at the beginning of their degree, and that course contains mostly material that's from year 11 and 12, a little bit of year 10 even, and a little bit beyond year 12. So it's a really kind of long stretching course. And that's difficult to teach, not because of the content, but because the students there often are quite frightened of doing mathematics. So that's the challenge in that course. The second part of what I do is research, and I'm going to talk to you a lot about that in a moment, and that involves finding interesting problems, solving these interesting problems, and then writing about what you did. Now, I think a lot of people will think of a mathematician stuck in a room by themselves in a cloud of chalk dust, and that's not really how it works. Most of the time, and most of the people I know work very collaboratively with lots of other people, and so yes, we're normally at a board, but normally there's 2 or 3 or 4 of us standing at a board all looking confused because we're not sure what to do next. The good thing about doing things collaboratively, apart from making lots of new friends, is I get to travel. People I work with are all over the world, and here's a picture of me at the Vatican when I was visiting a colleague of mine in Italy. So I've been really fortunate, at least in the before COVID times, to do quite a lot of travel. The rest of my job broadly falls under service and can involve all sorts of different things, peer reviewing, editorial roles for different journals, conference organisation. And as I get further and further in my career, it involves a lot more of working with teams of people to do different things. Okay, now I'm telling you about this because I want to make 2 points. The first point is that when I was in year 12, I enjoyed maths, but I never knew you could do it at uni, and I certainly didn't know that you could make a career out of it. Now, I like to think that we do a better job of telling younger people now that you can do maths and you can make a job out of it, and I'm not talking about just a job at uni or a job as a teacher of mathematics. And I'll tell you more about different kinds of jobs at the end. I like to think we're doing a better job of telling people about this, but I don't know if we are. The second point I want to make is that I think it's important to let young people know that they don't need to know now what they want to do for the rest of their life. I thought I wanted to do environmental science. It's not actually what I wanted to do. You never know what opportunities are going to arise that you never knew existed. And if they don't know what they want to do, my advice is always to choose something in the general direction that's kind of very broad, and then see how you go and see what things you enjoy. Okay, the second thing I want to do before talking about real world problems is just to acknowledge the fact that there is a lot of mathematics that has nothing to do with real world problems. Now, David Butler, who is here today, waving his hand around. If I can change the page. There we go. David Butler tweeted out this tweet earlier this year. He said, "Maths suffers a lot from being useful. Because it often is useful, people insist that it must always be, and it's a big burden to bear." Now, I wholeheartedly agree with this statement. Many times I've been asked by students, when am I ever going to use this? And I'm sure that science teachers and geography teachers and art teachers and music teachers don't get asked this question, and we get asked it all the time. And sometimes I just want to answer, and sometimes I do answer, maybe you're never going to need this, but isn't it cool? And isn't it interesting? And isn't it amazing that it just works out like this and it's just lovely? And I think that's a perfectly good answer. And if you want to read more about this, there's something that's quite old now, written by Paul Lockhart called A Mathematician's Lament, and some of the things he says in there are also along those lines. Okay, so now let's start talking about real world things. So what I'm going to do is I'm going to talk about a string of different problems that either I've worked on or friends of mine have worked on, tell you a little bit about the mathematics that was used, most of which is beyond school kind of mathematics, but hopefully indicate or give some suggestions about what kind of links you might have to mostly Year 12 and Year 11 mathematics. Most of what I'm going to talk about is differential equations because that's my background and that's kind of the area where I have the most experience. And the first few problems I'm going to talk about, actually, I was going to tell you what I do. After that slide talking about maths sometimes doesn't apply to the real world. Let me talk about this for a moment. My favourite thing to do in mathematics is actually nothing to do with the real world often. Sometimes it does have something to do with the real world, oftentimes it doesn't. My favourite thing to look at is nonlinear partial differential equations. Now these are equations that contain derivatives, and they contain derivatives that tell you how things change with more than one thing. So maybe things are changing with time and with space. My favourite thing to do is to find solutions to these equations, not numerical ones that you can find on the computer, but analytic ones that you can find and you can write down in terms of functions that we know lots about. The specialist technique that I use is called classical and non-classical Lie point symmetry analysis. And this is a systematic way to look for symmetries in the problem. So symmetries that might be like a rotational symmetry or maybe a reflection symmetry, but also those symmetries that you can't just see by looking, these really obscure kind of symmetries. And you can use those symmetries to kind of simplify the problem and to turn it into something that you can solve, and you can write down these really cool, complicated solutions to these nonlinear, tricky partial differential equations. Sometimes they have something to do with the real world and oftentimes they don't, and I think that's fine and it's still cool. All right, now I'm going to talk about real world stuff. Okay. The first problem I'm going to talk about is a scratch assay. This is a picture of a scratch assay at the bottom. I'm going to try and point in both directions sometimes. Now, if you look on the edges here, you can see that there are cells on the edges, and in the middle, there is nothing. So what's happened here is they've grown this little culture of cells in a petri dish, and when they're all happy and covered the whole dish, what they do is they get a scraper and they scrape away the ones in the middle. And then what they do is they watch and see how the ones at the edge move around and reproduce and recolonise that middle section. And the reason they do this is because it's a good representation of, for example, a wound. So a wound is like scrape the cells away. Let's see what happens when they grow back again. All right, now here is an equation that models this situation. So the U is going to be the cell population density. The cell population density depends on where you are in space and where you are in time. And then we can write down this equation that tells us what happens. So the left-hand side tells us how the population density is changing with time. And that's balanced by these two terms on the right. The first one is diffusion. That tells us about how the cells are moving around in the dish. And the second term here tells us about the reproduction of the cells. Now, there are actually two terms hidden in this reproduction term. The first one, the RU, is just linear in U. That tells us that births and deaths are going on. The second term here, which would be RU multiplied by U, that quadratic term, that's like a population limiting term that tells us that actually when there's no nutrients left or when there's no space left, there shouldn't be any new cells getting born. Everything's full. And so this is an equation that you can use to model what's happening when these cells recolonize. All right, I'm going to talk about a few population models and then I'll say something else. Okay, the second problem I'm going to talk about is Hirschsprung's disease. Kerry Landman at the University of Melbourne spent a long time investigating Hirschsprung's disease. So when in your gut, what happens is as you leave the stomach and as you go down your intestines and out to the end, there are these muscles along the gut that do squeezing and they push everything along and out the end. Now, what happens is with Hirschsprung's disease is you have these muscles along most of your gut, but you don't have any at the end, and so you can't push your poo out the end. Now, when you are, before you're born, when you're growing inside the womb, you start as a stomach, and then your intestines and your gut grows out of your stomach. And the cells, these neural crest cells that turn out to be these muscles that do the squeezing, start at the stomach and then they spread along the intestine and the gut as it grows. And so here what we've got is a picture of a chicken gut. Here's the stomach, here's the guts coming out. Time is going upwards, so you can see the gut gets longer and longer as time goes on. And these little black arrows are telling you where these cells, the neural crest cells, have reached at different times. And you can see that they haven't made it to the end yet, but hopefully by the time the chick hatches, these neural crest cells have made it to the end and they won't have Hirschsprung's disease where they haven't got these squeezy muscles all the way to the end. Now, there's very little known about how these neural crest cells that will turn into the squeezy muscles actually spread along the gut. So they didn't know, is it the ones at the front of the wave that are reproducing and spreading forwards? Is it the ones at the back near the stomach that are reproducing and pushing the others forward? Or is it a combination of both? And they could do some fancy experiments that I'm not going to talk about, and they could do some modelling, and they could look at the model and see which kind of model matches up with the experiments. So here is one of the models that Kerry wrote down. Again, we've got this U, which is going to be our dependent variable. That's going to be depending on space and time. And the equation tells us that the number or the cell population density changes with time, and it depends on diffusion. So this is cells moving about and spreading along the gut. It depends on reproduction. This is like the same term as we had before. We've got reproduction and then we've got a population limiting kind of term that says once it's full, we don't want any more. This term here is something that tells you about how the cells are carried along the gut as the gut grows. Okay, so we've got this extra term that moves them along as the gut grows. So V tells you something about how the gut is growing. And using this model, they were able to give some insights to the biologists about what's going on and how these cells are colonising the gut as it grows before people are born. Okay, the next one. I need some help. There we go. Okay, this is one of my favourite problems. This is one that I worked on, and this is one that I could use my specialist techniques for, that they actually, and it was actually applicable to the real world. So this is a picture of fertilisation of a sea squirt egg. So what happens when an amphibian egg is fertilised? And when I say amphibian, I'm being a little bit general. I'm meaning frogs and other kind of water-dwelling creatures. When these eggs are fertilised, what happens is there's a wave of calcium ions that comes out from the fertilisation point and moves around the egg, covers the egg with calcium ions, and what that does is it stops more sperm getting into the egg, because you don't want extra, you don't want polyspermy, and just ruins the genetics. So what this picture is this is a sea squirt egg. There's a fertilisation point down in the bottom right-hand corner here when T is 0. Those numbers are different times. And as time goes on, you can see this orange and yellow colour spread across the egg. So the orange and yellow is telling you that there's calcium ions there. So you can see these calcium ions spreading from the fertilisation point across the surface of the egg. Now this was observed in the 1980s. The first time it was observed was in the 1980s. Bless you. They wrote down this equation to model what's going on. You'll notice it's quite similar to the last ones that I showed you. This time U is going to represent the concentration of calcium ions. U depends on the angle. Let's say it's fertilised at the top now, not at the side. We're going to fertilise at the top. Theta tells you about how far around the egg you've gone. So the concentration depends on how far around the egg you've gone and what the time is. And the differential equation to describe what's going on is this one. So the concentration varies with time. This one here is a second derivative. So it's like the other diffusion terms that were on the previous pages, but I've used an upside down triangle here, and what's that is encoding? It's encoding the fact that instead of moving on a plane, we're moving on the surface of a sphere, okay? Same term as before, it's a second derivative, but it's encoding that we're on a sphere, not on a plane. This term here is talking about how calcium ions are released from the egg and how they're reabsorbed into the egg, and I'll talk more about that later. So they wrote this equation down in the 80s, they solved it numerically, great. A couple of years ago, only a couple of years ago, we figured out how to solve this analytically. We could write down an analytical function. It includes tans and exponentials and all sorts of things that you're familiar with, but it's quite long and complicated. And here's a plot of our solution on the surface of a sphere. So here's our fertilisation point at the top, and you can see the yellow and the red representing the calcium ions coming down over the surface of the egg. I was super excited by these solutions. All right, now this is a partial differential equation and it's nothing you could deal with at school, and that's fine, but you can look at this term here, right? This term here is just a cubic in U. U times by something with U times by something with U. It's just a cubic in U, and I've plotted it down here at the bottom. And you deal with cubics at school. And so what this is telling you is that the rate of release of calcium ions, so we've got the calcium concentration along here, the rate of release of calcium ions depends on the concentration. When there are no calcium ions, so here we're at the origin, then nothing's going on, nothing's getting released. As the calcium ion concentration increases a little bit, there's a negative rate of calcium ion release. That means it's being absorbed. So when the calcium concentration is low, you don't have a release of calcium ions, you have calcium ions absorbed. And then as you go past this critical value here, this U star, now the rate of release becomes positive and calcium ions are released. And so this is a cubic function, and you do a lot with differential calculus at school. And you can ask things like, where are the zeros? That's a little bit obvious from here, but you can ask that question. You can ask, what's the maximum rate of release? You can ask, what's the minimum rate of release? And what does that mean when it's negative? So there's some things you can talk about there using the kind of mathematics that's at school. Okay, the next problem I'm going to talk about, oops, too many, is another fertilisation problem. This is a fertilisation problem for mammals. So here is a picture of a bovine egg, a cow egg, after it's been fertilised. The egg is that circle thing in the middle, and around the egg are these nurse cells called cumulus cells, and they provide the egg with nutrients and oxygen and things before it's fertilised. Once it's fertilised, it doesn't need those cells anymore, and there's a calcium signal that tells all those cells around that they can die and they can move away. Now, if you look at the pictures, you'll notice at the beginning, the cells are kind of around the egg are dark grey, and at the end, they're a light grey. The light grey ones are dead, the dark grey ones are alive. Now, at the beginning, what happens is it's fertilised at the top, and if you look along to the top row, the last one in the top row, you can see that the cells at the top are light grey, and there's this kind of boundary here, and the cells at the bottom are dark grey. So there's a signal that comes out from the top of the egg where it's fertilised, and then it kind of goes down and around through the other cells, tells them they're no longer needed, they can die and move away. You can actually model this with the exact same equation as we used on the previous page, except for this time you're in slightly different geometry. The concentration depends on the angle down, but it also depends on the distance from the egg. And so that kind of different geometry is again encoded in this upside down triangle thing. But apart from that, the equation is the same. We can also solve this one numerically and analytically, and we can give the, the researchers that do these kind of experiments some idea of what's triggering these calcium signals. Is the egg doing it itself when it's fertilised, or is the sperm doing it as it comes through those cumulus cells and telling them all you're no longer needed? They don't know, but hopefully we can give them some insight. Okay, so all those problems that I just spoke about are broadly falling under the umbrella of population modelling. Maybe it's populations of cells, maybe it's populations of calcium ions. They're all partial differential equations, which you don't deal with at school. So these are equations that deal with things that change in space and in time. But what you can do is you can just say, let's just assume things only change in time. And now you've got, I might need some help. Whoop, too many pages now. Okay, and now you've got equations that you can start to think about, I think, at school. All right, so the first one I've written down here is an exponential growth model. So here what we're going to say is the rate of change in population size is equal to the rate of births minus the rate of deaths. That makes sense. We can write that down as an equation. How it changes in time is the births and the deaths. And I can combine those two terms. They're both just linear. So if I say m minus n is just r, some combination birth-death rate, then I've got an equation here that if I rearrange that, I can solve it just by anti-differentiation. It's just going to be, you're going to integrate it and get a log, rearrange it, and you're going to get an exponential, and that's going to tell you there's exponential growth happening. You can make this a little bit more complicated by introducing that population-limited growth that I talked about before. So in a population-limited growth model, the growth rate, instead of just being a constant, is this thing that I've written in orange, and I've drawn it in orange in this picture here. So this picture shows us the birth, or that combination birth and death rate, as a function of the population. In the first model here that we talked about, the growth rate was constant, so that's this blue line at the top here. In this second model, the orange one, the growth rate depends upon the population that's already there. If the population is small, then the growth rate is close to being the same as before. If the population is getting close to the carrying capacity, then the growth rate goes down to 0 because there's no more food, there's no more space, we don't want extras. And so you can write down an equation like this. Now this is just a quadratic function on the right side. You can ask all sorts of questions about quadratic functions. But also you can rearrange this one again and you can integrate that just by using anti-differentiation. That one's a little bit trickier and might need some hand holding, but I don't think it's beyond doable. Okay. There we go. Okay, so now I'm going to switch from talking about population models with one equation to models that have a system of differential equations. So the first thing I'm going to talk about is predator-prey models. Now predator-prey models, you can write down a word equation for them, and then you can write down an equation in mathematics that matches that word equation. So this example that I'm going to give is going to talk about rabbits and foxes. So rabbits I'm going to represent by X, and foxes I'm going to say are the Y's. And you can write down a word equation that says the rate of change in prey, so that tells you how it changes in time, is equal to the rate of births minus the rate of deaths minus how many of them get eaten. And you can write that down like this, the rate of change in the number of them with time, fine. The births, you're going to add them on, and that just depends on how many are there. The number of deaths, that just depends on how many are there. And the number that get eaten by the foxes depends on how many rabbits there are and how many foxes there are. So you just write down a term that goes like X and Y. The foxes, you can also write down an equation for them. So the number of foxes changes with time, and they're just going to have births and deaths. But in the case of the foxes, the births depend on how much food there is. So it also depends upon the number of rabbits. So the births for the foxes is a term like X and Y, and then they just have natural deaths as well. Okay, now there are online solvers. You can't solve this system of equations. There are online solvers, and you can play with the parameters, and you can see what happens if, you know, rabbits are born much faster than normal, and you can see how that changes what happens. And the online solvers will just plot the solution for you, and that's fine. But another thing you can do, oops, that's not what I want. Another thing you can do is you can look at the steady states. So steady states are when nothing is changing, and when nothing is changing, the time derivatives will be zero because nothing is changing. And there's a whole conversation I have with my students about what it means when there's a steady state and why should the time derivatives be zero when there's a steady state. But not only that, once you've set the steady states and you've set the time derivatives to be zero, what you're wanting to do is to investigate when these right-hand sides now will be equal to zero. And so what you're doing is you're looking for values of X and values of Y, or numbers of rabbits and numbers of foxes that satisfy those equations, and that will tell you what the steady states are. Now this is just solving a system of equations, but this time they're nonlinear. So I know at school you solve systems of linear equations, and you can do that by substitution, and you can do that by row operations on matrices. You can't do these ones with row operations on matrices, but you can do them by substitution. The interesting thing here, though, is when you solve these nonlinear equations using substitution, you don't get one solution, you can get multiple solutions. And then you can have conversations about what do these multiple solutions mean. Are the foxes and rabbits just living nicely together? Is one of them dying out? What happens if one of the steady states has like -10 rabbits? What does that mean? So you can have all these conversations about those kinds of things that are going on. Okay. Oop, too many. Okay. The next one I'm going to talk about is another systems of equations model. Before I do though, I'm going to tell you a story. In the 1990s and before that, New Zealand kept having these measles outbreaks. And when there was an outbreak of measles, there was about 50,000 cases. And in 1996, they came to a friend of mine, Mick Roberts, who I've written at the bottom of the screen there, and they asked him to do some modelling to tell them what was going on. Why did they keep having these outbreaks? They were vaccinating people, but they still kept having these outbreaks. So Mick did some calculations, and he predicted that an outbreak was about to start. Now, measles is a reportable disease, so there had started to be reports coming in of cases of measles, but they weren't enough for the health department to realise this is the beginning of an outbreak. He told them it's the beginning of the outbreak. They did a mass vaccination program, and that outbreak was limited to 2,000 cases instead of 50,000 cases. They asked him to do a little bit more work. Now, in New Zealand, they used to recommend vaccinating children at 1-year-old and 11 years old. It turned out that that was the worst spacing between vaccinations that they could have chosen, and that's why they were having the outbreaks. And so he recommended that they change the vaccination schedule for measles to be at 1-year-old and 4-year-old, and they haven't had one of these massive outbreaks of measles since then. In Australia, they vaccinate, or they recommend vaccination at 1 and 4. I think that's really a happy coincidence rather than any clever planning. But you know, we haven't had those same outbreaks back then that New Zealand did. Okay, let's talk about the modelling. So when you do disease modelling, they often do that with things called compartmental modelling, where you stick people in boxes. And the number of boxes you have depends on the type of disease that you're modelling. So I'm going to show you two different ones. The first white box here has got two boxes. There's an S box and an I box. S stands for susceptible and I stands for infected. So as a person, you're either susceptible to this disease or you're infected by this disease. And you can see in this model, you can go from susceptible to infected, and then you can go from infected to susceptible. So this is the kind of disease where you get sick, and then when you get better, you don't have any benefits of immunity. You just go straight back to being susceptible again. The one at the bottom has 3 boxes and lots more arrows. This one has a susceptible box, so you can be susceptible to this disease. You can be infected by this disease, or you can be, R stands for removed. Now, removed might be recovered, or it might be dead, but you're removed from the population once you're in that box. And there's lots more arrows. There's lots more arrows. So this one's saying that you can be born in this model, and when you're born, you're susceptible to the disease, so you go in the susceptible box. And it's got these 3 arrows at the bottom, so this model is including natural deaths. So anyone can die of natural causes, and you could come from any box. So this model has a lot more going on than what this model here does. When you write down what's happening in terms of equations, you can also see what's going on. So this tells you the number of people in the susceptible box changes with time, and that's balanced by the number of people going out of the susceptible box. That's why there's a negative, because people are going out. And the number that go out depends on how many susceptibles there are and how many infected people there are, right? If there's more infected people, you're more likely to get infected and move to the next box. And then this part here tells you can move back into the susceptible box when you get better from being infected. And the infected equation is kind of like exactly the same, but the opposite signs, because the arrows are going in that direction. This model is a bit more complicated. The one at the bottom, you can be born into the susceptible box, you can move out of it if you get infected, or you can die of natural causes. And you can just go through all those equations and you can see what's happening. Now again, this is a system of equations that you can't solve, but there are a lot of online solvers that you can look at and play with. And I think that this is really useful because you can set it up like a model that's easy to understand with these boxes and arrows going from one place to the other. And you can see how to build the model. I'm just going to show you one of the online websites, if I can get... Yeah, great, awesome, thank you. Okay, so here is just one in GeoGebra. There's this one in GeoGebra. I think there's probably some in Desmos as well. But what this is doing is it's solving the equations I had on that slide, and they're written in here. I mean, we can't see them because they're going behind that thing there. And all the parameters for the model are down here, but they've actually built in these sliders too. So you can say, I want this many births, and the disease makes you die at this rate, or you can recover at this rate, or so on and so forth. And you can see what's happening here. So the blue line is the number of people in the susceptible box. And at the beginning, there's lots of those. The red line is the number of people infected. At the beginning, it looks like 0. It's not 0, it's just a few. The green line are the ones that are removed, and that starts at 0. And you can see what happens very quickly is the number of infected people go up, the number of people in the susceptible box goes down, and then people start being born, and the susceptible line goes up again. And now there's so many susceptible that more start getting infected. And you can see that this is like an initial outbreak, and then there's these waves. Now, we've all seen lots of these kinds of graphs in the last few years. And these are things that we can all relate to. So if you change these parameters at the top here, you might get these subsequent outbreaks, or you might not get these subsequent outbreaks. Okay, can you go back to my slides, please? Great, thank you. So these are the kind of models exactly that we use to model COVID as well, and to predict what would happen under certain lockdown conditions. The models for COVID, though, were, of course, much more complicated. They had boxes for adults, boxes for children, boxes for within households, boxes for between households. And they spent an awful lot of time determining what the parameter values should be under different conditions, but it's the same kind of model. Okay. Oh, here we go. Okay, the next one, whoops, that one, yes, thank you. The next one, I'm not going to talk about the mathematics very much, but I am going to talk to you about it because I think at year 12, when you start doing complex numbers in spec maths, it just seems like some purely imaginary, useless thing, and why would we ever bother having it? But actually it is useful. Why would we bother having it except that it's beautiful and lovely? So there's this thing called the Joukowsky map. So when you build, you can all see, this looks like the wing of an aircraft, right? When you build an aircraft, it's really tricky to model what happens with the air going over the airfoil because it's a really tricky shape. But there's this map that uses complex numbers. It's called the Joukowsky map. And what it does is it turns a cylinder, so this is if we're looking down a cylinder, turns a cylinder into the shape of a aircraft wing, okay? What you can do then is you can do the modelling of the air flowing past a cylinder, which is much more simple, and then you can transform the shape, that cylinder shape, into the shape of an aircraft wing, and you can transform the airflow into the airflow past an aircraft wing. And this is done with complex numbers. It's a complex mapping. And can you just go back to can you go to the second website, please? Okay, so there's this website that talks all about the Joukowsky map and the Joukowsky airfoil. I'm not going to go through it, but if you could scroll to the bottom, please. Okay, here's the flow going past a cylinder, and can you change the shape? You can just play with this and you can change the shape of the cylinder to an airfoil, and you can see how the flow goes past that different shape. Great, and can you leave it on the airfoil? Now, the other thing I want to talk about is there's this thing called the Bernoulli principle. When fluid is flowing faster, it's at a lower pressure. The fluid here is the air. When it's flowing faster, it's a lower pressure. If you look what's happening with the air at the start, at the front of the airfoil, right, it has to split upwards and downwards, and then they have to join back together with the ones they were previously holding hands with at the same time. Now, the distance over the top of the wing is longer than the distance underneath the wing, and so the speed up to get past that little curve at the end, but the ones at the top are going much faster than the ones at the bottom. So that's a kind of really interesting application of a mathematical subject or topic that just seems completely abstract at year 12. Okay, yep, can you go back, please? Thank you. All right, next page. Okay, I'm not going to talk very much about the mathematics of the next two problems. Is that really 5.2 already? In fact, I won't talk about this one at all. I'm going to go to the next one. Can I go to, yep, that's it. Okay, so this thing called the pitch drop experiment, it was set up in 1927. What they did was put pitch in this little jar at the top there. Now, pitch is like tar. It's a fluid at room temperature, but only really just. They let it settle for 3 years, then they nipped off the bottom of the funnel and let it drip out. It took 8 years for the first drop to fall. They missed it. They missed the second one. They missed the third one and the fourth one and the fifth one and the sixth one. The seventh one, this is the second custodian of this experiment. He was there watching the seventh one, dashed out to get a drink of water. They missed it. After the seventh one, they installed air conditioning in the building, and you can see the time between drops increases because it's colder and it's more viscous, so it takes longer to drop. They installed a camera so that you could watch it. It failed when the 8th drop fell, so they missed it again. When the 9th drop fell, it was stretching down and they got worried that it would touch the previous drops that were already in the beaker before it actually snapped off. So they took the beaker out, put a new one in, but they bumped it. So it snapped off. And if you could just go to that last website. Yep, that's it, great. You can actually watch what's happening. Slightly more exciting than watching grass grow. But you won't be alone watching it. I can't see the number at the top, but the number in the top left-hand corner tells you there's 13 other people watching today. So this is the experiment at the University of Queensland, and you can sit and wait and watch, and there's the drop and the previous ones in the beaker at the front, and you can watch very patiently. And that's it. Sometimes you see people peering through the glass. Okay, can you guys go back to my slides, please? Great, thanks. So this seems kind of frivolous, but actually modelling this kind of thing is really important. Now, on the left-hand side here, I've got 2 drips. The first one, the golden one, is glycerol. That's really runny. Now, there's a lot known about how this drips. It's going to pinch at the top of that sphere. It's also going to pinch at the top of that thread. The thread's going to contract and make another little droplet. There's a lot known about when and where these pinches are going to happen. The next picture is honey dripping off a spoon, and you can see that it makes a really different shape. It's much longer, and we know from putting honey on our toast that these threads are really persistent, they're really long and really thin, and there's much less known about these ones, much less known about when they're going to break and where they're going to break. Now, again, who cares where your honey breaks, apart from the person who cleans up in the morning. But this picture on the bottom right-hand side is a picture down a fancy fibre optic cable. So they can now make these fancier fibre optic cables that have this internal structure, and this internal structure allows them to carry much more information than what a normal standard fibre optic cable can do. Now the way they make these is they make this glass preform with some kind of internal structure. They heat it up in a drawing tower and then they stretch it right down until it's long and thin, and they wind it up until it's kilometres and kilometres long. And this is exactly the same as what's going on with the honey, but this time you don't want it to break because you want it to be nice and clean and long and thin. These kind of things that seem a little bit frivolous actually have really kind of important applications. Another completely different question is the shape of the internal structure that you have in that preform is not the shape of the internal structure after you've stretched it. And so what kind of structure do you put in the preform to get what you want in the fibre optic cable? And Hayden is the person who's an expert on that. Hayden Tronalone, he spent a lot of time thinking about that over the last few years. Hayden's here too. Okay, I'm going to very quickly, I have to finish at 10, right? Yeah. Okay. I was just going to tell you a little bit about what we do at UniSA that shows students what happens in the real world. So in the real world, you get a problem and you don't know you don't know how to solve it, and often you don't even know what the question is. What we do at UniSA, they have a year-long project where they work in a team with industry and 2 academics to solve a problem that the industry brings to us. It takes you 2 months to figure out what the question is. And this is a really different experience for students who are good at maths, who are used to looking at a question that's written by a teacher or by an academic, and they know that there's an answer and they know that they know how to do it. They've just done the theory for it. It's a very different experience to take 2 months to actually figure out what is even the question. How do you write it down? How do you find a solution? Most of the time, the way to solve the problems is using a technique that they didn't learn in their degree, so they have to go and find the right technique and learn it. They've got 2 academics to help them. We often don't know either, and we have to learn something new. So it's this kind of really uncomfortableness, and you just have to sit in that uncomfortableness and think about what's going to happen next. We get all sorts of problems. I was going to talk about some of them, but I won't. From Woolworths, about reorganising their warehouses, about aquifer management, how do you pump water into the aquifers and out of the aquifers, and what does that do to the aquifers, and so on and so forth. I'm happy to talk about them later if anyone wants to ask me. And I'm going to leave this slide here and I'm not going to talk about it, but here are some interesting jobs that other friends of mine in mathematics have. You'll see I've got teaching and a university academic at the bottom, but there are lots of really interesting jobs in mathematics around, and I think it's really important to communicate that to our students. I'm happy to talk about these too if you like, or anything else. If you ask me, I might just blabber on. Be prepared for a long chat. That's all I have to say.